This is supposed to be the last lecture on economic growth, and I hope it'll be the first where we get a little bit into depression economics. We want to try to do a bunch of things, but first let me start out with what I hope will be the last logistical commercial. That is the current situation. We don't have more people who want to take the course than we have seats. The only reason that people are not yet in the course is because they're trying to get into a section that's already full. If this is your problem, go up and see Joan Kask at the International and Area Studies office and get it resolved. Otherwise, simply switch your section online and you should be absolutely fine. Right? The waiting list should have cleared by now. We shouldn't have people still on the waiting list. Problem set 2 is due right now with this pile up here at the front. Answers to problem set 2 will go out this afternoon onto the web as soon as I proofread them one more time, because it's really embarrassing to make arithmetic errors in your problem set answers. And yet it always happens that you do so, no matter how many times you've taught the course. And in the future, please write down your name and your section time on your problem sets, because that's going to make it much easier for Dariush Shahedi to get the problem sets back to people in a timely fashion, if he can sort them by the pile of when people are attending their sections. Now, problem set 2. The economic growth parts of courses like this are always regarded as the hardest and most difficult and most confusing. Nevertheless, I'd like to know people's reactions to problem set 2. What do people think of it with respect to the way to spend what really looks like it was the first week of spring here in Berkeley, California? Okay, all right. Point taken. Point taken. I have two reactions. First reaction is that this is supposed to be the finest public university in the world, and we want to keep it that way. And assigning long and hard problem sets is a good way to do that. Second is that yes, that when those of us who teach courses like this get together to gripe and talk and gossip, one of the things that we perennially chew on when we have these discussions is whether we should be including economic growth in the syllabus for this particular course at all, or whether that should be shoved off to another course. Precisely because the material is somewhat harder than the material taught in the rest of the course, and not all that closely related to the material taught in the rest of the course. Greg Mankiw, now at Harvard, got us into this business a generation ago, when he wrote a very good intermediate macroeconomics textbook that for the first time moved the economic growth material front and center. Ever since then, pretty much everybody has followed Greg in their syllabuses. It's not clear to me we're doing you a great favor. On the other hand, if we don't teach this stuff in intermediate macro, it then tends not to get taught, and it is very, very important. They said problem set 3 will go out today, and I'm not sure whether to make it a half problem set or not. It depends on how far I get today. If I get as far as I want to get, it'll be a full 10 problem set. If not, I'm going to take a chainsaw to the text this afternoon, or just after lecture, and chop off the bottom half of it, and postpone the depression economics, the business cycle economics part of the problem set until next week, because you won't have covered enough material. That's my current thinking. I'll tell you at the end of the lecture what it's going to be, because we are about to start the depression economics unit of macroeconomics, which is right and proper. Right now, the economy is in a near depression, and this course should spend a lot of time on the current situation. But as I go over what I want to do and what the likely pace of events is, it looks as though I'm not going to have time to do enough backing and filling over the financial crisis and its consequences in lecture as I want to. So I'm going to make Dariush and his sections talk about the financial crisis. And for that, I'm going to want you to read alongside the textbook what I think is the single best book on the recent financial crisis and its implications out there that exists, Bethany McLean and Joe Nocera's If All the Devils Are Here. So watch your email box for assignments from McLean and Nocera before your next section starting, say, next Thursday, because I'm going to want you to be talking about the financial crisis and about Nocera and McLean in sections, and those discussions will go much, much better if you've read the book beforehand. General Bethany McLean is really great. She's also one of the authors of, I think, the best book on Enron, the Enron scandal of the early 2000s, which is also worth reading. And Joe Nocera may be the best kind of personal financial reporter that the New York Times has ever had. The book gets great reviews. It's extremely readable. It's exciting. Often financial books are quite boring, even though they involve large amounts of money going places where they shouldn't, which is usually something that perks up our interest. But Nocera and McLean make this thing very, very readable indeed. With that, let me move on to recapitulations, things that you really should know. And one thing that took me a little bit aback was that the end of the problem set appears to have been a bit harder for you all to get than I thought likely, which means that I'm going to have to think hard about how to teach this better. Now, I remember back when I was a junior, I had these high-powered physics major roommates while I was a political economy major, and they persuaded me that what I really wanted to do was come along with them to their quantum mechanics course and take it pass-fail along with them on the grounds that they would help me do the problem sets and they would make sure I wouldn't flunk, and anyway, it would be amusing to watch me try to deal with the material. I agreed, so I went and I did, and I actually learned some quantum mechanics, and actually at one point derived the base orbital of the electron in a hydrogen atom with the Schrodinger equation. Not that I could do it again today, but it was worth doing. The problem was that after the first midterm, the professor Edward Purcell, the inventor of magnetic resonance imagery, winner of the Nobel Prize in Physics, assorted other things, stood up in front of the class and was really, really depressed because the class's performance on the midterm had, he thought, been really, really awful. Why, he said, one student didn't even know, and then he proceeded to give my failed answer to one of the questions on the midterm. And I almost raised my hand and stood up and said, "Don't worry, Professor Purcell, I'm not a real physics major. I'm just a political economy major who's been kidnapped by my roommates and forced to take this course. I really don't know what I'm doing." But I didn't have the guts to stand up and do that. And so presumably his confidence in his abilities as a teacher were greatly shaken by me. And I'd like to apologize now, which I haven't done before. But seriously, when people are having as hard a time with problem 8, say, on problem set 2 as they have, it's time for me to stop and go back over what I expected and what I thought would happen in class. So here's our problem set 8. We have Botswana. We have Botswana in the 1950s, before independence from the British Empire, having an extremely low savings rate and being an extremely poor country. Today, Botswana is a middle-income country, one of the richest countries in Africa. The question that problem 8 is trying to get at is, how was this accomplished? And so this problem A has 4 parts, and the first of which asks you to move into an imaginary counterfactual alternative universe world to try to figure out what would have happened in Botswana if things had been more or less the same except for growth in the efficiency of labor. How do I expect you to do part A? Well, the first thing I expect you to do is to write down kind of the basic growth equation for what determines output per worker. Or in this case, since we don't think the labor force is moving very much as a percentage of the population, output per capita is going to be a pretty good guide to what's happening to output per worker. And our major determinants of the level of output per worker for an economy on its steady-state balanced growth path are 3. First, there's the efficiency of labor, this thing E here at the far right. Second, there's the capital intensity of the economy, the term inside these parentheses. And third, there's the speed with which diminishing returns to investment kick in, the speed with which adding more capital and becoming a more capital-intensive economy really doesn't help you very much because you're adding extra capital that's not very useful. And that depends on this diminishing returns factor. That's this little exponential term up here. And the capital intensity of the economy, well, that's the quotient between the savings investment effort the economy is making, its savings investment share of GDP, this variable S, divided by the sum of the country's labor force and population growth rate, N. How much of your new investment is required to simply get your new workers the capital stock they need to produce at the normal level for the economy. The depreciation rate, delta, this little Greek thing, this D with a hooked tail, how much investment is needed simply to replace the capital that wears out, and this labor product, this efficiency of labor growth rate, G, which you need there because if you have a great deal of growth in the efficiency of labor, that's going to need more capital in order to keep the capital output ratio constant as well. So you write down this equation, and you say, what do we know? And you say, well, we have 2 dates. We have 1960 and 2010. In 1960, we know what our economy-wide level of productivity is. It's given as $900. We know what the savings share is. It's 6%, 0.06. We know what the diminishing returns factor is. It's 1/2, so you get 1/2 over 1 minus 1/2. That's going to simply drop out. You know what the rate of population growth is. You know what the depreciation rate is. The 2 things you don't know are what the rate of growth of the efficiency of labor was in 1960 and what the level of the efficiency of labor was in 1960. But you can write down everything else in the equation and do what you can to simplify it and get something that looks like this for 1960. For 2010, well, you know it's on its balanced growth path, so you know this is the form to use for capital intensity. You know the savings rate, you know the diminishing returns parameter, you know the population growth rate, you know the depreciation rate. You still don't know what the efficiency of labor growth rate has been, but you do know that you're moving into this alternative universe in which the efficiency of labor in 2010 is no bigger than the efficiency of labor in 1960. So whatever the efficiency of labor was in 1960, it's the same as 2010, same in 2010. So that means this is your equation for 2010. So at this point, you'll notice you don't have quite enough information to solve these equations for the answers you want to get. And I was taught by my teachers that this is actually the best way to ask students to write down problem sets, or to do problem sets. Because if you don't give them quite enough information, they then have to make extra assumptions, which means they have to think hard about what the equation means. So expect always, or often, that there'll be one little piece of information missing before you can get your answer, and you're going to have to make an assumption about it. Here, there are 2 possible assumptions you can make, or 2 ways you can proceed. The first is to say we've moved into an alternative universe in which we're supposed to assume the efficiency of labor isn't growing between 1960 and 2010. That means we can simply assume that the rate of growth of the efficiency of labor is 0. That after all, it tells us not to grow, that it's not going to grow at all. So we can just substitute 0 in for the efficiency of labor wherever it appears. And if we do that, then this term is simply 1. The efficiency of labor in 1960 is simply equal to this GDP, this overall prosperity term. And we know that the efficiency of labor in 1960 is 900. If we do that, then this term here is 5. We know the efficiency of labor in 1960 was 900, so we have 900 times 5 equals 4,500. We see that output per worker in 2010 is 5 times, or output per capita in 2010 is 5 times what it was in 1960. That's our answer to part A. The second road you could take would be close to the same, a little bit clever, would be to say we have a couple of numbers we don't know in each equation. But suppose we look at the ratio between prosperity in Botswana today and prosperity in Botswana in 1960. We know our output per capita figure in 1960 was 900. We know that we have the same term. We have the capital intensity in 2010 at the top, times the efficiency of labor, the capital intensity in 1960 at the bottom, when we divide the prosperity in 2010 by prosperity in 1960, times the efficiency of labor in 1960. These 2 terms cross out. 0.30 divided by 0.06 is 5. And so then we have 5 times these 2 remaining terms left over from our arithmetic. And if we're just willing to assert that the rate of growth of the efficiency of labor is the same in 2010 as it was in 1960, after all, we haven't told you anything about it changing, so that's a reasonable assumption to make, these terms will cross out too. And if those terms cross out too, you're left with, well, you had this 5 here, and you had, for the capital intensity, and you had this 900 here. So then output per worker in 2010 is going to be 5 times 900 is going to be 4,500. Same answer, gotten 2 different ways. One way is by saying we really don't know quite enough to solve any of these equations, but if we're looking at growth between 1960 and 2010, we do know enough to solve for what the growth is between 1960 and 2010. And we're given where things were back in 1960. Second way to do it is to say, well, we need to make an extra assumption. And since we're considering a universe in which the efficiency of labor isn't growing, assuming that G is 0 is a fine thing to assume. Either of those would be fine. 8B then. How fast has the efficiency of labor grown in Botswana over the past 50 years? Well, we've just calculated that if the efficiency of labor had not grown at all, Botswanian GDP per capita today would be only 4,500. It's actually 15,000. That's an extra growth factor of 3 1/3. Right? 15,000 is 3 times 4,500, and that factor has to come from a growing efficiency of labor. Right? We already took account of increases in the savings rate, etc., in saying that it would have been 4,500 if there had been no growth in the efficiency of labor. So that extra factor of 3 1/3 has to come from a growing efficiency of labor. If there's no place else it could come from, how fast does something grow if it grows to 3 1/3 times its initial value in 50 years? This is what God made the logarithm key on your calculator for, or the y to the x key. The logarithm key if you're an engineer, the y to the x key if you're an accountant. So you want something to grow to 3.33 times its initial value. That equation is 1 plus the growth rate raised to the 50th power. you take the natural logarithm of both sides, and then the nice thing about the natural logarithm is that if you have an exponential inside, the exponential simply gets pulled out to the front. In logarithm land, raising something to an exponential power is the same thing as multiplying the logarithm by the exponential power in front. Your calculator tells you the log of 3.33 is 1.203. That's equal to 50 times the log of 1 plus the growth rate g. And the other very nice thing about logarithms is that as long as your g is relatively small, as long as it's a percentage less than 20% or so, there's absolutely nothing wrong with simply saying the log of 1 plus g is equal to g itself. That's what the logarithmic function does as long as g is small. So you have 1.203 equals 50 times g, which gives you a labor efficiency growth rate in Botswana of 2.4% per year, on average between 1960 and 2010, which is quite good, but actually not all that much faster than the United States. That in Botswana has been growing very rapidly, but not because it's been catching up a huge amount to the United States. Yep?
Can you explain the part about
As meaning why is log of 1 plus g equal to g if g is small? Well, if you found that your answer was g equal to 1, then you'd have to go back and say, wait a minute, I need to do this differently. But in general, if your answer says that g is less than 20%, it's fine. But if it's bigger than 20%, if it's bigger than 0.2, then you really shouldn't be saying log of 1 plus g is equal to g. I think the intuitive understanding is the logarithmic function is related to the difference between compound interest and simple interest. And if your interest rates are small, there isn't much difference between compound interest and simple interest. And so there's not much difference between g on the one hand and the log of 1 plus g on the other. If you try to expand out, use calculus to expand out what this function actually is, you'll see that if you expand out the log of 1 plus g, you get a g, and then you get other extra terms that have g squareds and g cubes and g to the fourth in them. And if you take any number that's a lot less than 1 and square it, it becomes really, really small. And if you cube it, it becomes really, 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 really small. So you can say if you use calculus to expand out what the function is, the idea that when g is small, log of 1 plus g is almost exactly equal to g comes immediately out of unpacking what the function is. The deep answer is this is the way the logarithmic function was defined. That if it hadn't worked out that way, we'd have thrown it away and chosen another function. Because part of making the logarithmic function useful is that log of 1 plus g is about g when g is small. It's just a tool, and it's kind of something you should have in the back of your minds. If you're engineers, at least, if you're accountants, you kind of do it a different way by using your y to the x key. Okay. Let's see. Let me see if I can pull up the right program here. Yeah, here we are. Okay. Okay. What we have is 3.33. We want a growth factor of 3.33. This really isn't large enough. Big answer? Well, that's not much help. Preferences. Will preferences help? Appearance? Yes, we can make our fonts bigger. Okay, hopefully that will work. And now let's get rid of the big answer. Well, that doesn't seem to have worked. Oh well, 3.33 was what you wanted to get. You wanted to figure out what the growth rate was going to be. That was going to get you, no, that's not what we want, equals 1 plus some growth rate raised to the 50th power. So the right thing to do then is if you want to raise the growth rate to the 50th power, what you should then do is you should take the growth factor and you should raise that to the 1/50th power. And that's going to be equal to 1 plus your growth rate. And so then you can subtract 1. And that will give you your growth rate of 0.02435 of 2.435%. That is your equation back on. No, it's not there. Not there either. Not there. Not there. No, this is the right program, but the wrong slide, the wrong course. Right? Your equation was this 3.33 equals 1 plus g to the 50th. And in order to get rid of the 50 up there with your y to the x key, you want to take the left-hand side and raise it to the 1/50th power. That will, raising both sides to the 1/50th power, will knock out the 50, and then you'll be left with 3.33 to the 1/50th power equals 1 plus g, and then you just subtract off 1, and you get the growth rate. For problem C asks you what was the value of the efficiency of labor in Botswana in 1960. And once again, here I think there are two ways to do it, which are about equally good. The first would have been to say, what do you mean? I already did this for part A. We assume that the growth rate of the efficiency of labor was 0. Then that means that this term is 0. We have 0.06 over 0.06. That means that E 1960 was $900. We already did this for point A, or part A. And that would be okay. The second thing would be say, wait a minute, we just did our calculations in part A, assuming that the growth rate of the efficiency of labor was 0, because that's what part A asked us. And then in part B, we found out that really wasn't quite true, that the growth rate of the efficiency of labor instead was 0.024, at least between 1960 and 2010. The problem doesn't tell us, but what if we assume that back in 1960, the efficiency of labor growth rate was the same as we turned out to calculate between 1960 and 2010? Then we have a 0.024 here for the growth rate of the efficiency of labor. And so we don't have a 1 for the capital intensity of the economy. We have a 0.72. And that means our efficiency of labor is $1,260 in 1960 rather than 900. That's a reasonable answer, too. That's an answer we'd be very happy with. 900 and 1260 aren't the same, but they're not that different in the context we're talking about, which is the context between the difference between 900 and 15,000 for the relative prosperity of Botswana. So that's what we were looking for C. And then for D, what's the value of the efficiency of labor today? Well, we know what the value of output per capita in Botswana is today. It's 15,000. We already calculated 0.024 for the growth rate of the efficiency of labor. We have 0.3 for the savings investment share. We have 0.02 for the population growth rate. We have 0.04 for the depreciation rate.